So this lecture is going to give you a quick overview on data analysis and some of the statistical concepts used in operational research. And what I'm going to do in a flash is to go through presentation of data, samples and sample size, some of the simple statistics with some examples. We'll touch confidence interval, precision, p-value, the chi-square, and a little bit about risk ratios and odds ratios, and maybe we'll end up with survival curves. So presentation of data. How do you present your data? The first thing you need to really think about is the objectives of the study. And you need to try and imagine what your data should look like after the analysis and how you will present it. In other words, the kind of tables and figures and etc. So if you cannot, by looking at your objectives, imagine how you would present your data, you really need to go back to objectives and think again about it, because they might not be specific enough. Now here's a simple table as a way of presenting data. And it shows new TB cases per year in Malawi between 1985 and 2003. And you see on the left side, on the left side column, you have the year between 1985 and 2003. And on the right, you have the TB cases. And you will notice there's been an increase, in fact, an exponential increase in TB notifications between 1985 and 2003. 5,335 to over 25,000 cases. Now this is linked to the HIV/AIDS epidemic. We had our first cases in 1985, and HIV considerably increased the notification of TB cases, particularly in sub-Saharan African countries such as Malawi. So this is one way of presenting that data. Now if you look at that exactly same data, presented as a figure, you will agree with me that it is much more expressive in showing a rising trend in TB case notification rates over time. The key message, or the key take-home message, is that when you plan to do your tables or figures, think carefully on what is the best way, or what is the best figure or table, or whatever other means you may be using, to convey the message you want to emphasize to your audience. Let's move on to a sample. Now, a sample is defined as a representative group of subjects. For example, TB patients, smokers, vegetarians, sampled from a population so that you can make inferences on the whole population. It's often because you can't do studies on the whole population, you want to take a sample to make those inferences on the whole population. I'll give you an example. Let us assume that we want to look at the proportion of men in a town who smoke. We then interview a random sample of 1,000 men, and we find 200 smokers within the sample. Therefore, the proportion of smokers in the sample is 200 divided by the total you sampled, 1,000 people, so that's 20%. And if you want to make that inference on the whole population, you want to say the proportion of smokers in the town is therefore 20% plus or minus a sampling error. It's as simple as that. Now, sampling is the process of selecting those subjects from a population with the aim of using the information provided by the sample to draw correct conclusions about the source population. So a key issue is that the samples must be representative of the population or the source population so that you can avoid bias. The term sampling power is the probability of finding a difference in a research study to be statistically significant when this difference actually exists. So an 80% power means that you have 80% probability of finding a difference. The key message here is that the power of a study is increased by increasing the sample size, and I'll come back to that. Now you can do sample size calculations using a program called Open Epi, which is available freely on the net. You can Google it and then download it, put it in a USB key, and try this exercise yourself. Using a question, what is the HIV prevalence among TB patients at a site X? Once you've downloaded your Open Epi software, open it, go to sample size on the left, select proportion, and then fill in the data. You need to define the population size, and we'll assume here that it's 1,000 new TB patients a year. You have to put in the estimated or anticipated frequency of the factor. So this is the prevalence. It's a real guess, because if you really knew what it was, you didn't need to do a study. And we'll assume it was 70%. And then the precision, which we normally leave at 5%. And the sample size, to be able to detect that 70% with a 95% confidence interval, will be 245. Try that yourself. You can also do sample size calculations using Open Epi for cohort studies. Please go through this. You again open Epi. You can open up your Open Epi. You go to cohort or randomized controlled trials, RCT, and you enter these different results. Try it, and if you got it right, you should have the required sample size of exposed and unexposed 737 E on each side or on each arm. That would give you roughly 1,474 TB patients for a cohort study. That was actually the sample size we used in the study with the reference in blue. Confidence intervals and 95% confidence intervals. Now, what is a confidence interval? Well, a confidence interval is a range of values within which the true population parameter is believed to be found with a given level of confidence. So the rationale for calculating confidence intervals is the uncertainty which is always associated with using samples to make inferences on populations from which these samples originate. So it's a little bit in other terms, the sampling error. So a 95% confidence interval simply means that we can be 95% confident that the true population value lies within the limits that you actually find. So I'll go back to that study on HIV prevalence in TB patients at site X, and we said we used a sample of 245 TB patients, and we found an HIV prevalence of 70%, and the 95% confidence interval was 64 to 76. What does that mean? Well, it simply means that we can be 95% confident that the true HIV prevalence among the TB population would lie anywhere between 64% and 76%. Let's move on to precision, which is a term that you often hear about. Now, it can be used in two senses. The first is the number of significant digits obtained for a measurement. For example, if you took the height of a person, you could record it as 1.734. That is more precise than 1.7 meters. Now, you rounded up the significant digits in the second example. Now, is that important? Should we be recording 1.734 or 1.7? It really depends on what you're looking for. If you are in a height competition, then you would like to use the first. If not, you might just use 1.7. The important issue about precision is to ask yourself, when you put in those significant digits after the decimal place, is it relevant? Is it important? So importantly, when you report, avoid putting spurious or unnecessary precision. It clogs up your tables. The other way we use precision is the reference we make to the magnitude of the standard error or the sampling error of a measurement. Now, in other words, the precision is the width of the confidence interval. Now, wide confidence intervals stem from small sample sizes, and if you remember, I had said earlier on, with bigger sample sizes, you have better power, you will have better precision. And I'll demonstrate this with two examples. Let us consider that we've done 2 prevalence surveys for malaria. And in the first survey, we found 10 people with malaria on a sample of 100. That's 10 divided by 100, which is 10%. And the 95% confidence interval for that parameter would be 5 to 18%. We run a second survey on the same population, but this time we find 100 people with malaria, but our sample size was much bigger. It's 1,000 people. The prevalence we find for malaria is exactly the same, 10%. But what happened to the confidence interval? You notice it has narrowed from 8, and in the second example, it's between 8 and 12. So there's a considerable narrowing of the confidence interval. The important message here is that if you increase the sample size, your confidence interval narrows, your precision therefore improves. The p-value, you've all heard of the p-values. It's a significance test, and in the context of significance tests, for example, the chi-square, the p-value expresses the probability that an observed difference would occur by chance alone. Small p-values indicate stronger evidence of difference. Now, p-values are generally expressed as less than or equal to 0.05, which is actually our cutoff for statistical significance. If it's less than 0.01, it's very significant. And if it's less than 0.001, it's highly significant. This is how you should express your p-values. You should not express p-values simply as significant or non-significant. You should actually put in the numeric value. Now here's an example of p-values looking at 2 groups, the characteristics of patients in a cotrimoxazole arm as against a control arm. And you would see as you go down the table that smear-positive TB, PTB, is significant, less than 0.01. Smear-negative pulmonary TB is significant. And if you went to the TB category, new TB case and other is significant. And then you also have a number of significant variables, the first 3 in the type of TB treatment. For the rest, they are not significant, because the cutoff is 0.05. Now, the chi-square test is very often used, and this is a significance test for comparing 2 or more proportions from independent groups. Exactly the kind of example I've just covered in the last slide. And here's an example, and again, you could use the Open Epi to actually do chi-square calculations. You open your software, you go to Counts, and then you select 2 by 2 table, and you enter this data as it is. If you want to look at group 1, smear-positive TB, whether that percentage is any different from group 2, you enter this data, and you should be able to get these p-values that I have got in this slide. Let's move on to risk ratios or relative risks. Now, these are used in cohort studies, and by definition, it's simply the ratio of the risk of an event in one group that was exposed or offered an intervention, be it TB treatment, antiretroviral treatment, whatever, to that in another group which was non-exposed to that same kind of treatment. Now, you get relative risks in cohort studies. Now, a risk ratio of 1 that you get from a cohort study means that there is no difference in risk between the two groups that you compare. A risk ratio greater than 1 suggests there's a greater risk of the event in the exposure group compared to the control. And a risk ratio less than 1 suggests a protective effect of the event in the exposure group. So greater risk, protective effect, and these two parameters are decided upon based on whether they're over or under 1 in terms of the risk ratio. Let us try and look at this in relation to heart disease. Now, there are several risk factors for heart disease, and these include smoking, high blood pressure, high cholesterol levels, diabetes mellitus, and obesity. There are also additional risk factors for heart disease, and these include the lack of exercise, an unhealthy diet, stress, and a type A personality. I don't know if you know what a type A personality is. It's someone who is emotional, who is impatient, and aggressive. We won't go into all those details. Let's just take the relation of smoking and heart disease. And we will try to look at relative risks. Now, when you're looking, you get relative risks in cohort studies. And in cohort studies, you assign your exposures and you follow up the patients over time and you see how many developed the event of interest, in this case, heart disease. So it is research looking forwards. So in this example, 65 smokers who were followed up over time developed heart disease out of 110 who smoked. The risk of heart disease in smokers is therefore 65 divided by 110, or 59%. Similarly, among non-smokers followed up over time, 30 out of 90 developed heart disease. The risk of heart disease in non-smokers is thus 30 divided by 90, which is equal to 0.33 or 33%. The relative ratio or the risk ratio can be calculated quite easily by dividing 0.59 by 0.33, which is 1.8. And that is comparing risk of heart disease in smokers to the risk of heart disease in non-smokers. And what this means is that smokers have a 1.8 times higher risk of developing heart disease than non-smokers, or in other words, an 80% higher risk. And that's how you interpret this. Let's move on to odds ratios, which you get in case control studies. And an odds ratio is a ratio of two odds. And you get odds ratios from case control studies. Now, the difference with cohort studies is that in a case control study, you start with the outcome and you go back and you look at the exposures. In other words, research in reverse. It measures the ratio of odds of exposure among those cases to the odds of exposure among controls. Let's go back to that same example of heart disease and smoking. This is now an odds ratio, so it's a case control study. You start with heart disease and you go back and you look at how many of those with heart disease smoked as against those who did not smoke. So in this example, out of all those who had heart disease, 65 were smokers, while 30 were non-smokers. The odds of smoking or the exposure among those with heart disease is therefore 65 divided by 30, 2.1. Similarly, among those without heart disease, 45 were smokers, while 60 were non-smokers. The odds of smoking or the exposure among those without heart disease is therefore 45 by 60, and that is 0.75. The odds ratio, comparing the odds among those with and without of smoking, among those with and without heart disease, is 2.1 divided by 0.75 or 2.8. In other words, among patients with heart disease, the odds of smoking is 2.8 times higher compared with those without heart disease. Please don't look at the numbers I've used in these examples. They are too small for cohort studies, but you've noticed here that actually the odds ratios are much higher than the relative risk. And this often happens if the condition is quite common. Now here's an example in this table of how relative risks are actually displayed. This is looking at treatment outcomes in patients with new smear-positive TB in Tiolo district compared to a different district, Mulanje in Malawi. And you see a relative risk of 1.3 for treatment success. This implies greater risk of treatment success since it's over 1. Here's the relative risk of death of 0.7. It's under 1, and this is thus a protective effect against death. And you have the confidence interval in green. So how do you interpret this? Treatment success, a relative risk of 1.3 with a 95% confidence interval of 1.2 to 1.4. It simply means a 30% greater risk or chance of success in the intervention group compared to the control, and we are 95% confident that the real risk would lie somewhere between 20 to 40%. A relative risk of death of 0.7 means a 30% lower risk or protective effect of dying in the intervention group compared to the control, and we're 95% confident that the true value would lie anywhere between 10 and 50%. Can you tell me what a relative risk of 5 means? Well, it means 400% greater risk, or a 5 times greater risk. Now here's a table looking at risk factors associated with very early deaths among patients started on antiretroviral treatment, and you would see here a relative risk of 1.2, but the confidence interval crosses 1. It is 0.8 to 1.8, and we say that is not statistically significant. So any relative risk that crosses 1 is insignificant. In the second example further down, you notice in green a relative risk that is over 1, 1.4 to 3.3, and that is statistically significant. You can also do relative risks using Open Epi. You open up the software, go to counts, go to 2x2 table, you enter the data, and try to do that with the example I have just shown you in the previous slide. Finally, a little bit about survival plots. You've probably heard about the Kaplan-Meier survival curve. This is a plot showing survival probability over a period of time in study groups, and you use this in cohort studies. The log rank test is another significance test to compare if the survival curves between the two study groups is statistically significant. So if you saw something like this, and you can find this in the reference provided in the title, you would see the cotrimoxazole arm, which is the upper curve, and the control arm, which is the lower curve, and it simply means that everyone starts on the left side with 100% survival, and as time goes on, time in months is on the x-axis, people are dying. And in the cotrimoxazole arm, there is a better survival effect, or more people are surviving, less are dying, than in the control group. And if you look at the Cox-Mantle log rank test, which is a simple significance test in the middle of the plot, it is very highly significant. That is simply the key aspects of the anatomy of a survival plot.